Hello everyone, and welcome to a final discussion in our universal gravitation unit of orbits and energy. So here we have an object of mass m in a circular orbit, a distance r from the center of the Earth. We're going to assume, of course, a perfect orbit with no air resistance. Right? Of course, the only force acting on that apple would be the force of gravity, which acts towards the center of the Earth. And so as we put it in orbit in a circle at a constant speed, the force of gravity always points inward. Now, in terms of energy, since it's moving, this apple would have a kinetic energy equal to 1/2 mVo squared, where Vo is the orbital speed of the apple. In a previous video, we derived an expression for the orbital speed of a circular orbit, which was the square root of big G m over r, where m is the mass of the thing being orbited, in this case the mass of the Earth, and r is the radius of that orbit, the distance from center to center, essentially. If we plug that in for the orbital speed, and then square, we get a kinetic energy equal to big G, mass of the planet, mass of the object, all over 2r. So there's an expression for the kinetic energy of a circular orbit. Not really something I want you to memorize, but something I want you to be able to get to, right, if needed. Right? And by the way, you could very easily, if you know the speed, right, you can just use the original equation. This would be only if these were the things you knew. Now, remember that the gravitational potential energy of a mass a distance r away from the center of a planet is negative big G mm over r. So if you notice here, the kinetic energy of something in a circular orbit is the opposite. It's positive instead of negative, and it's 1/2 as big. Right? So for a circular orbit, the kinetic energy is negative gravitational potential over 2. It's 1/2 the gravitational potential energy. Again, not really something you need to memorize. Because it's only true of circular orbits, it's fairly easy to tease out, right? Now let's talk about the total mechanical energy. This is going to get a little more important. So of course, total mechanical energy is the sum of the kinetic and the gravitational. So as we just saw, the kinetic energy for a circular orbit is big G mm over 2r. And the gravitational potential energy we derived in a previous video is negative big G mm over r. Remember, the negative comes about because this only shrinks to 0 at infinity, and we are under infinity. Right? So it's always negative. Put those two together, and we get negative big G mm over 2r for a circular orbit. This is the total amount of energy. So you need to know the mass of the planet, the mass of the object, and the radius of the circular orbit, which is the distance from the center of the planet to the center of the object. But note, look at this, and look at kinetic energy. They're the same, just opposite. So weirdly, for a circular orbit, the total energy is the negative of the kinetic. Again, a little factoid, not something to memorize, right? Just something to recognize, if need be. Now, I'm going to do something that I don't normally do, which is to assert something without a proof. Essentially, the total energy of an elliptical orbit is the same as the total energy of a circular orbit if you replace the radius with the semi-major axis. Okay, my feeling or proof for this is kind of a Kepler's third law thing, where we've kind of already done that, where we've taken the semi-major axis and the radius and kind of used whichever one was appropriate. Right, for a circular orbit versus an elliptical orbit. So this is the total amount of energy. Okay? Now, on an AP test, they don't expect you to know this equation. If they ask you to find the total mechanical energy, they expect you to do something like this. Take the kinetic and find the gravitational potential, right, and add them. And in fact, they probably expect you to do the kinetic as 1/2 mv squared, as opposed to this, which we got by using the orbital speed and plugging it in, right? Just depends what you know, right, and what you can use. You do have to be really careful, though, if you are going to pull this equation out for a test, that this is the semi-major axis. And so you have to make sure that you know the semi-major axis to be able to use this, right? Otherwise, you kind of have to go back to just your basic definition of total mechanical energy. We're going to use both of these in a problem here. So here's the example we're going to do. Two small spaceships, each with a mass of 2,000 kilograms, are in a circular orbit of the diagram at an altitude h of 400 kilometers. Note that means a distance above the surface of the Earth of 400 kilometers. Igor, the commander of one of the ships, arrives at any fixed point in the orbit 90 seconds ahead of Sally, the commander of the other ship. Now, this was a problem I actually took out of an older version of your textbook. Back when I used the same textbook or a very early edition, right, when I was a physics major, this problem was in the chapter on universal gravitation as an example. They actually worked this whole problem out. Now, it lives in the question section at the end of the chapter, and they've stripped out all what I think are the fun parts, which you can tell that this question was written during the Cold War, right? So you've got Igor, obviously, right, a Russian, who's ahead of the plucky, astronaut Sally, so stereotypical American name, right, who happens to be 90 seconds behind. And you'll see what Sally does through the course of this problem. Now it just says, one ship is ahead of the other ship, and it doesn't, use the names or anything. But I like the old version. It's so Cold War. So we're going to do a whole bunch of things here, okay, with this problem. So let's start out by figuring out the period of the orbit. Now, no, we're not given a lot of information here. Right? Yeah, we know that Igor ends up 90 seconds ahead of Sally at any point, but that doesn't help us figure out how far he went around. But note, they are two objects which are orbiting the same mass. Oh, and that sounds like something that we could apply. Right, so they're orbiting around. That sounds like something we could apply Kepler's third law to. Right? And this, remember, is our full version of Kepler's third law that we actually derived in class. Yes, it holds the proportionality. The period squared of the orbit is proportional to the cube of the semi-major axis, or in this case, the radius, because it's a circular orbit. But it allows us to just look at one object at a time, right, because of all the constants that we put in there. Right? We actually derived this by applying the law of universal gravitation to circular orbits using the centripetal acceleration, if you remember. Right? So we can use this to find the period of either ship. Because notice, the mass of the ship doesn't factor in here. This is the mass of the planet, the mass of the thing being orbited. So if we solve for the period just by taking a square root of both sides, of course the square root of 4 pi squared is 2 pi, so I factored that out, right, just to make it look pretty. And then we got to be careful. R is either the separation distance from the center of the Earth to the center of a spaceship, or it's the radius of the orbit, which is the same thing in this case. But neither of those are 400 kilometers, because that's the altitude. That's the distance above the Earth. Why did they say it that way? Well, because that's commonly the way we talk about satellites, right, or spaceships. We say, oh, they're in an orbit of this, when we're really talking about is how far above the surface of the Earth they are. And so you got to be a little careful with the language. If it had said orbital radius of something, right, then that would be r. But instead it said altitude h. So that means h is how far above the Earth you are, right? So we have to take the radius of the Earth, which is like 6.37 times 10 to the 6th meters, and we have to add h, which is 400 kilometers, which is 400 times 10 to the 3rd meters, which is 4.0 times 10 to the 5th meters, which when you add it up gives you 6.77 times 10 to the 6th meters. Right? So that's the r in this case. So be careful with the way the problems are stated. Right? Do they give you r, or do they give you something that you can use to calculate r? So obviously if this was an actual AP problem, they would have had to have given you the radius of the Earth, because that's not a number they would expect you to just have at the tip of your tongue. Right? So plugging all those numbers in, see, here's our actual r, here's our gravitational constant, here is the mass of the Earth we derived earlier, a little less than 6 times 10 to the 24th kilograms. Don't forget the 2 pi out front and the square root. We get a period of 5,540 seconds to 3 sig figs. Note, all of these numbers are to 3 sig figs. Right? So 5,540 seconds is the period. Kepler's third, a handy little relationship to have when talking about orbiting objects. Okay. Now, I want to know the ship's orbital speeds, how fast they're going. Two ways we could do this. The other day, we derived an expression for the orbital speed of a circular orbit. Big G, mass of the planet, all over the radius of the orbit. We know all those numbers, so plug it in, and we get an orbital speed of about 7,680 meters per second. So that's one way to find the answer. Legitimate, great, right? Second way to use it to find the answer would be to use what you found in part A. Because it's moving in a circle, right, at constant speed, wouldn't the orbital speed just be the circumference over the period, right? The distance one time around divided by the time one time around. And we have those numbers, and not so surprisingly, you plug them in, you get the exact same answer, of course. This one might be a little better to use from a problem-solving technique because it only uses constants, right? And this one uses the previous answer. So if you somehow got part A wrong, right, you just get part B wrong too. So, but either way, right, gets you to the same answer. Total mechanical energy of either ship. I can do this either ship because they're the same mass and they're at the same radius orbit, right? Well, two ways to do this. We could use this equation that the AP doesn't expect you to know with the radius of the orbit in here because it's a circular orbit. Plug all the numbers in. Notice our 6.77 times 10 to the 6th here, right? Not just the 400 kilometers from center to center, the radius of the orbit. And we get negative 5.89 times 10 to the 10th joules. Total mechanical energy. This certainly works, but it's not the way the AP would expect you to do the problem. The AP would expect you to do the problem by finding the sum total of the kinetic energy and the gravitational potential energy. The kinetic energy being 1/2 mv squared, and the gravitational potential being negative, so it's plus a negative, right? Big G mm over r. Plug in all of those numbers, and not so surprisingly, you get the exact same answer. Now, would the AP mark you wrong if you did it this way? No. As long as you plugged in the right numbers and got the right answer. Right? And the key here is that you got to have the right R, right, in order to get this all to work out. Okay? Notice this uses something you found earlier, so they would kind of expect you to use that. So they would probably give you full credit if you got part B wrong, but you used it correctly in part C. Okay? And notice it's a negative total amount of energy, which is kind of interesting, but that has to do again with our negative gravitational potential energy due to our zero being at infinity. So now Sally does something. She wants to win the race, right? The plucky American astronaut. So she does something perhaps a little counterintuitive. She fires a little burst at point P in the diagram. So if we go back to the diagram here, right, at point P, she's going to fire her rocket. But she's going to fire it in a forward direction, which reduces her ship's speed by 1%. She actually slows down. Why the heck would she do that? Well, let's see what this does. Part D, let's find her new kinetic energy and her new potential energy immediately after the burst. So before she does anything to her orbit, right? So basically she's at point P, okay? Well, her kinetic energy would be 1/2 m times her new speed. Her new speed would be 99% of her old speed. You see how I did that? She reduced it by 1%, right? So 0.99 of the speed you calculated earlier. And don't forget that's squared, and this you square this whole thing. So her kinetic energy is now 5.78 times 10 to the 10th joules. Her gravitational potential energy at point P is exactly the same as it was before, because she's still the same distance from the center of the Earth. So that works out to be negative 1.18 times 10 to the 11th joules. What's her new mechanical energy, total mechanical energy? Well, add those together, and you get negative 6.02 times 10 to the 10th joules. Now, let's compare that to her original mechanical energy before she slowed down. Okay? So negative 6.02 times 10 to the 10th now. Before she slowed down, negative 5.89 times 10 to the 10th. Is this one smaller or bigger? Well, the coefficient's smaller, 5.89 instead of 6.02, but these are scalars and it's negative. So it's a smaller negative number, right? Which means the original is bigger, and this is actually less total mechanical energy than before. Which I hope makes sense, right? She didn't change her height. She slowed down by 1%. So I hope you would think, oh, that means she should have less total mechanical energy. But remember, because we're in negative scalar land, that means a more negative total mechanical energy. Okay? And that's what the numbers tell us. Negative 6.02 instead of negative 5.89, right? Times 10 to the 10th, same order of magnitude. Okay, so bigger negative means less mechanical energy. So that means she's going to change her orbit. Okay, so what would her new semi-major axis be immediately after this burst? Well, the only way to do this is to use our special equation we kind of half derived for the total mechanical energy, using the semi-major axis here. All right, so if we solve for the semi-major axis, and we plug in the new total mechanical energy, and all the other numbers we knew, notice here, m is the mass of her ship, which is 2,000 kilograms. We're dealing with very big and very small numbers, right? We get a semi-major axis of 6.63 times 10 to the 6th meters. Well, knowing this number, knowing the radius of her previous orbit, which of these two orbits is she going to fall into? Again, let's compare those numbers. This is her new semi-major axis. The radius of the original orbit was larger. With me? So which one of these, one or two, they're both elliptical orbits, right, has a smaller semi-major axis than the original radius? It is, of course, orbit 1. So by slowing down, she will dip closer to the planet, right, and go in this new elliptical orbit. With me? Okay. So what now will her new orbital period be? All right, in this elliptical orbit. Well, again, we can use Kepler's third, but now we have to use the semi-major axis of her new orbit. All right, take the square root, plug in all the numbers, right, and we get a period of 5,370 seconds. Okay? So now when she gets back to point P, she goes around once, gets back to point P, is she ahead or behind Igor still, and by how much? Well, Igor's orbit period, orbital period that we calculated right at the very first part A, is 5,540 seconds. Sally's new period with her new smaller semi-major axis is only 5,370 seconds for a difference of 170 seconds. And remember, she was 90 seconds behind. So if she gains 170 seconds on him, she'll end up 80 seconds ahead. And she'll win. Ah, the plucky American astronaut Sally beating the evil Soviet Igor, right, in their race in the stars. But notice here how she won, right? She won by slowing down, right, which put her in an orbit that basically whipped her around the planet because she dove closer to the planet, which is going to speed her up, right? So it took less time to go in this orbit. If she would have done the obvious thing, if she would have fired her rockets forward, speeding up by 1%, she would have gone in that other orbit, which was bigger. It would have taken her even more time to get around once, and she would have ended up farther behind. So she won by slowing down and by being smarter. Ah, the plucky astronaut. Rocket science is tough, right? You got to deal with all the negatives and the big numbers right? Kepler's laws and the law of universal gravitation and all the things we find, and elliptical orbits versus circular orbits, which means semi-major axes versus radii, can all be done. It's just got to be done really carefully and paying attention to what each and every quantity means, right, in the problem. So she won by slowing down. So here they are, trucking around, trucking around. Sally's behind, thinking about whatever should I do? I must get ahead of the evil Soviet Igor. So I'm going to dip. Whoop! I'm going to go around, and there we go. Right, back ahead of him. So she fires a burst to slow down, whips around the planet, fires some speed back up, and she ends up ahead of him and wins the race. Good job, Sally. Good job.